Okay, folks, it's time for the next online lecture. Um, Today, the plan is to discuss linear magnetic materials and ferromagnets, which are nonlinear magnetic materials. And the important concept today will be to discuss the concept of magnetic susceptibility, which is basically this idea that if I have a magnetic material, then if I turn on an H field, then that's going to cause the magnetization to rise, to become non-zero. And remember, this whole concept of a magnetic material is just this idea that I have a material, remember, with a bunch of current loops in the material. And those current loops give rise to magnetic dipoles, which I'll draw as these little arrows. Those are magnetic dipoles, M, and that creates magnetization, because magnetization, remember, is the number of little dipoles in a small volume divided by the volume. And the volume is not the volume of the whole material, but just of a little region of the material at some location R. So M is a position-dependent vector field. Okay, so how does the magnetization change when I turn on an H field? That's what we want to understand. And before diving into it, I want to remind you, I always do this. I sound like a broken record, but I really want you to see the analogies between the electrostatic case. Because when we treat magnetostatics, it's always perfectly analogous to how we treat electrostatics. And so the electrostatic case is, remember, for the electrostatic case, we had polarization. Remember, instead of magnetization, we have polarization. And remember how we said that we had to define this new D field, because D field equals epsilon naught E plus P. Remember? And the reason we define the D field is because the divergence in the D field equaled the free charge. And let me fix that. And we also, it was important because this allowed us to also define, we also defined bound charge, remember? And the bound charge, divergence in the bound charge, bound charge creates divergence in the polarization vector. And of course, if we have of course the total charge creates divergence in the electric field. And so this is why we invented the D field, because that's what created divergence. Because the free charge creates divergence in the D field. And then and then we went on to define for a linear material. Let's say linear material. We define the polarization as for a linear material, the polarization is epsilon naught chi sub E, the susceptibility, times the electric field. We defined that, and where chi is some number, and then remember we then were able to do a little algebra, which is very simple, by saying D equals epsilon naught E, and then here I have the polarization up there, and so that polarization then becomes epsilon naught chi sub E, and then I can say this equals epsilon naught 1 plus chi sub E times E. And so then we said D is equal to epsilon, the permittivity of a material E, where epsilon, the permittivity, is equal to the vacuum permittivity times 1 plus the electrical susceptibility. And so that was very useful. Remember, we did all that. And then remember we said that E then is equal to D divided by epsilon, and epsilon is always bigger than 1, and so that means that and so that means that epsilon, that the electric field is reduced. due to polarization. The electric field is reduced, and that's why we call insulators dielectrics, because they go against the electric field. Okay, so that was the electrostatic case, and that's just review. But now I want you to see, we're going to do the same damn thing now for the magnetic case. And I think it's useful just to sort of follow that logic. It's the exact same logic, only now the math is ever so slightly different. And so now for magnetic materials, what we do is we start with this idea that I define a new vector field which gives me curl in where I say that the free current creates curl in this new vector field, which I call H. And H, of course, is our old friend. I'll write it here, that we just defined in the last lecture, 1 over mu naught B minus M. And you look at it, and it seems a little bit weird when you first look at it, but the reason it has that funny look to it is because the important thing is that the curl of this new vector field is equal to the free current, and that's where that expression comes from. But by the same token, we can see that B is equal to mu naught H plus mu naught M, the magnetization. And this kind of makes sense intuitively because, remember, we think of H as sort of like the applied field, and then M is the magnetization response. And the magnetization is usually in the direction of the applied field, remember? Because we have a current loop, it has some magnetic moment, and if I turn on a B, then the magnetic moment goes in the direction of B. And we also know that the induced B field of a current loop is proportional to the magnetization. And so the idea is that I apply an H field, and the magnetization goes in the same direction. And so if there's some B field, I'm sorry, I'm having a little trouble here. Oh yeah, there it goes. I got stuck in the wrong mode. If the B field is like this, then we see that the magnetization is in a direction. Well, actually, I should call that the applied H field. So if the applied H field is in this direction, then we can see that the induced B field is proportional to it, and so the magnetization adds to the H field. That's why I have a plus here. All right, and so then we also can see that this allows us to define the magnetization allows us to define a bound current density, and we see that the bound current density causes curl in the magnetization vector, and we also know that if we just add up the total current, then the total current creates curl in the B field. And so total current creates curl in the total B field, bound current creates curl in the magnetization, and free current creates curl in the H field. And that's exactly the same as over here in the electrostatic case, where the total charge density created divergence in E, the bound charge density creates divergence in P, and the free charge density creates divergence in D. I just want you to see the analogy between these two ways of treating electrostatics and magnetostatics. And so now what we can do is we go through this, we do the same kind of argument, and we say we assume that for linear materials, and it turns out that there are lots of linear materials, then for a linear material, then what happens is the magnetization is proportional to the H field. And so that where this is a constant, and that constant we call the magnetic susceptibility. Magnetic susceptibility. And so this is, and it's often very small, typically small, such as 10, for example, it's 10 to the minus 5 for aluminum, and it's material dependent, because it depends on the current loops in the material and how they line up with the magnetic field. So here we go back to this idea here, and we have all these little loops and with their magnetic dipoles, and the question is, how do they line up when I apply a magnetic field? And if they line up a lot, then that this number is bigger, but if it's hard to line them up, then the number is smaller. And how they line up depends on quantum mechanics and all this complicated stuff that we won't get into. But we'll just assume that all that complicated physics is sitting inside of this constant. All the quantum mechanics and fancy physics is sitting inside of that constant, and we're just going to assume that the response of the material, the magnetic response, is linear in the applied field. And that means that I can plot this. I can plot that the magnetization as a function of applied field is a straight line. Very simple. And the slope of this straight line, of course, is this magnetic susceptibility. All right, well, if we have a linear material, then life is sweet and simple, because then we can do some very simple algebra, because we can write down that if I have the B field, then I know that the B field is equal to mu naught H plus mu naught M from the definitions that we did up here, right? And then what I can do now is I can just substitute in here, I can substitute in chi m h. And if I do that, then we get this simple expression that B is equal to mu naught H plus, whoops, what was that? Plus mu naught chi sub m h, which then means that B is equal to mu naught times 1 plus chi sub m h. Oh my God, look at that. B is proportional to H. And so then we say that B is equal to mu times H, where mu, which is now the permeability of the material, is equal to mu naught 1 plus chi. I'll put a box around that. And so mu equals, that's not m, that's mu, is equal to the permeability of the material. And I just want you to see the similarity between the magnetostatics case and the electrostatics case. You see, it's the exact same treatment, the same reasoning, the same idea. So it shouldn't seem strange to you. And so basically, what we see then is that B, the magnetic field, is equal to mu h, and now we see from the definition of mu, we see that mu is big. Mu is typically greater than mu naught. Actually, that's what I should have written way back here. This should have been epsilon greater than, greater than epsilon naught. And so what mu is typically greater than mu naught, because materials, because chi m is typically greater than 0. And so that means then that B is typically bigger than H. So the magnetization increases the B field, typically. And so that's different from the electric case, because for the electric case, E is typically less than D, since the polarization decreases the electric field. So this is a difference between the two cases. I just want you to see that. And this is for, and here I should say that for a paramagnet, for the paramagnetic case, then what we have is chi sub m is greater than 0, and then we have mu greater than mu naught. But some materials are diamagnetic, and those are the materials for which chi sub m is less than 0, in which case mu is less than mu naught. And that makes sense because for a diamagnetic material, then the m is opposite the applied field. M is opposite B. But most materials are not diamagnetic, so that's a less common situation. Most materials are paramagnetic, just in the real world. And I will just say that there are materials called mu metals, which you might have heard of. A mu metal is a material that becomes very magnetic. It has a really big mu. And those can be very useful for magnetic shielding. Okay, so that's the definition of the magnetic susceptibility. And so now let's, and how we use the magnetic susceptibility, it really comes down to this permeability. And we've derived this very simple relationship that B equals mu H, where mu is equal to mu naught 1 plus chi sub m, and this should remind you, of course, of D equals epsilon E, where epsilon equals epsilon naught 1 plus chi sub E. Same concept. Okay, so now let's use it in an example. And so let's consider an example. And for the example, let's do our favorite thing. So remember when we did electrostatics, we would always, the most important device geometry is the capacitor, and we would put material into a capacitor. Now, for magnetostatics, the most important device geometry is a solenoid. And so what we do is we put material into a solenoid. So let's do that. So here's a solenoid. Let's see, how should I do this? Let's draw the solenoid first. Solenoid. Here's a solenoid. Basically just a corkscrew of wire. We'll pass current through it, and the current, of course, is the free current. That's the definition of free current. It's the current that flows through wires. And now we're going to put a material into it. And let's put a cylindrical material into the solenoid. We often call this the core, and it's a magnetic material. And this magnetic material, let's see, I'll draw it like this. So there's a material in there, and that magnetic material is characterized by, we could either, typically it's characterized by a magnetic susceptibility, chi sub m. And chi sub m is something you look up in a book. Like if it's, I don't know, if it's cobalt, iron, or whatever, you look it up. Or if it's copper or God knows what, whatever the heck it is, you chi sub m is a number you look up in a book. And chi sub m can then give us mu, because mu is, of course, mu naught times 1 plus chi sub m. So if someone gives you chi sub m, then that's the same as giving you mu. So sometimes people give you mu, sometimes they give you chi sub m. It doesn't matter. It's the same thing. And let's suppose that here we have n turns per length. And so the question that I'm going to ask you is, what is the magnetic field inside? What is it? inside the material. And so I've given you chi and n and I free. What is the magnetic field inside the material? So what we'll do then is so the way to go about these problems is the first thing you notice is if there's free current. If we have free current, then you know that there's going to be an H. So if free current, then there's going to be an H. And it's useful because we know that del cross H is equal to J free. And so that means the integral form of that equation, of course, is the famous Ampere's law, written in this way: H dot dl is equal to I free enclosed. Right? Because that comes from the differential equation, then gives us the integral equation. And so since there's free current, we immediately get, what we want to do then is use this to find H. If we have free current, then let's find H. And so to find H, we'll do our Amperian loop. And really this is meant to, the idea is that this material fills up the material. Let's assume the material fills the solenoid. I did not draw it well, but that's the assumption. The material fills the solenoid. And so now we just do our little, and this Amperian loop has a height L. And so then by symmetry, we assume that the H field is pointing in this direction, H, by symmetry. And so then we have H, L, and that outside, it's 0 by symmetry. And so HL is equal to I free, which is simply N times I, because there's N, because there's going to be because if this Amperian loop is of length L, then there's going to be N. Oh, I'm sorry, it's NL times I. So that's the number of loops. That's the number of current loops in my Amperian loop. So then the L's cancel, and we get H is equal to Ni. So that's nice. But then I ask you for B, the magnetic field. So this is the applied field that we just calculated, the applied field. And now we can find the total field is B, and we know that B equals mu times H, where mu is just mu naught 1 plus chi m times H. And so that's it. We're done, because we know what H is. So B is equal to mu naught 1 plus chi sub m, where H is N times I. So now I can put a box around it. Yay! And we can see that B is bigger than H. So B is typically bigger than H if chi sub m is greater than 0, which it typically is. For most materials are paramagnetic. Okay, so all right, so that's sort of all that I want to say for linear materials. So that's sort of the situation for linear magnetic materials, and you can see how the treatment is very similar to the treatment of linear dielectrics. But now what we're going to do something different. We're going to talk about now let's talk about nonlinear materials, nonlinear magnetic materials. And this is a discussion that we did not have for the electrostatic case. And the reason is because there do exist nonlinear dielectrics. They do exist, but they're not as important or as prevalent as nonlinear magnetic materials. I mean, people do use nonlinear dielectrics for all kinds of important things, but but they're not as common or as important as nonlinear magnetic materials. And a nonlinear magnetic material is a ferromagnet, for example. A ferromagnet is a nonlinear magnetic material. And why is that important? Well, really, one of the most important things is that we this is how we make refrigerator magnets. And it's very important because often we want to leave a note for someone on the refrigerator saying, hey, don't leave the milk open, or hey, stop drinking my beer, asshole, or something like that. And so the ferromagnets are very important for leaving notes on refrigerators and for other things as well. You can imagine if you want to make, for example, a magnetic motor or whatever. Ferromagnets are very important. And so let's talk about, and a ferromagnet is an example of a nonlinear magnetic material. And so let's discuss this a little bit. And so why would a material be nonlinear? And what makes the material, remember our discussion of paramagnets, remember we were talking about, if I have a linear magnetic material, then the idea is I have all these current loops, right? And then they might be aligned in different directions. And each of them, and these are the magnetic moments. And the important concept is that the magnetic moments are independent. The M's are independent. They don't feel each other. And so when you turn on a magnetic field, they tend to just line up, each doing their own, just each lining up. They're just interacting. They only interact with the heat bath. They interact with the heat bath, and so their behavior is thermodynamic, and you, to understand it, you have to do statistical mechanics, which I won't discuss here in any detail, but that's the idea. And that's sort of it's the thermodynamics that's then determining the magnetic susceptibility. Chi sub m comes from stat mag. But in a nonlinear material, something different happens. I have two magnetic moments, and they feel each other. In a nonlinear material, the magnetic moments feel each other. I'll put an arrow between them. The M's feel each other. I feel you, and the M's feel each other. And so how do we think of that, using equations in physics? Well, what it means for two things in physics, what it means for two things to feel each other, is that there's an energy of interaction between them. And so the energy of interaction we'll call U. And the idea is, the way of thinking about it is that you can sort of think of one magnetic moment creates like a magnetic field that the other one feels. So we'll call the magnetic moment felt by one is, let's say, M for the ith magnetic moment. We can think that it makes a magnetic field like this, and then the second one feels it. And so that's the energy of interaction. Because you guys remember, one way of thinking about it is that you guys know that U is equal to negative M dot B. So if I have a magnetic moment sitting in a magnetic field, then the energy is negative M dot B. So if I have two magnetic moments next to each other, you can think that one creates an effective B field that the other one feels. And so there's an energy of interaction between them. This is a way of rationalizing it in your mind. Now where does that be effective comes from? It's complicated. There's lots of physics there. There's lots of quantum mechanics and complexity that we will ignore. But we'll just assume that in some situations we'll just take it for granted that there is an interaction between the magnetic moments. And so we can think of I and J as nearest neighbors. Nearest neighbors. For example, in a material, they might be atoms, and they would be the adjacent atoms as one example. And so what that means then is if I have U is equal to negative J mi dot mj, little j, then if j is greater than 0, and it often is, then what happens is you can see that that this is an energy that makes mi and mj, they want to be parallel, because you can just look at it and see that that's the case, because if for this energy, if mi and mj are parallel, then mi dot mj is a positive number, and if j is a positive number, then the energy is negative, and negative is good. Energy wants to be negative, and so there's a force causing the mi and the mj want to be parallel. Now, what happens if the m's are all parallel? Then what do we get? If m's are all parallel, then of course we get a magnet. Yay, that's what a magnet is. The thing that sticks to your refrigerator, that's a magnet. And let's draw a magnet. This is a magnet. Dun, 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 I'll draw a long skinny magnet, and these I'm drawing now the little m's, all the little magnetic dipoles in it are parallel. So this is a magnet. And the reason that they're all parallel is because of this interaction between them. And this interaction, we often give a name. You can call it, this interaction, we can call an exchange interaction. I'll draw it up here. Often we call that an exchange interaction. And don't ask why we call it exchange interaction. It gets kind of tricky. Lots of quantum mechanics is there, but we'll ignore that because we don't need all those nuances to understand this. So the thing to understand is just that there's an energy that causes that an interaction between the magnetic moments that causes them to to want to be parallel, and so that's a magnet. Yay! But it gets a little tricky because you can imagine that. Remember, this stuff is all at kT. It's all in everything is in a heat bath, and so this energy, so U is fighting kT. And so the thing that makes this not want, the thing that makes these magnetic moments not want to align is kT, the thermal energy. And so you can sort of see that, and the thing that determines the strength of U is J, right? Because U is equal to negative J mi dot mj, and so you can see that if kT is way bigger than J, then you can see that the alignment is screwed up, because now the thermal energy is bigger than the energy that wants to align them. And so if kT is way bigger than J, then you're going to get random. You're going to get random magnetic moments. And so the idea then is that there's a critical temperature, and that critical temperature is determined by J, critical temperature, and it's actually complicated to find out what that critical temperature is. There's a lot of details and nuances in stat mech and quantum mechanics, but let's not worry about all those details, and let's just realize that there's a critical temperature Tc, and Tc is going to depend on J. If J is big, Tc will be big. If J is small, Tc will be small. And so if my temperature is greater than Tc, that means that the randomness of the heat bath wins, and all my magnetic moments are random. They're just pointing in random directions, because now the temperature wins. And temperature, as you know, is random. It's all about entropy and randomness. And so we get and so then the magnetization of the material is 0. But if I have T less than Tc, then J wins. So here, KT wins. That's the Boltzmann constant. Let me write that more carefully. K sub B T wins. But if T is less than TC, then J wins. And the material becomes ferromagnetic, and they all line up. Yay! And then we can stick it onto our refrigerator. Yay! Magnet. So now the magnetization is greater than 0. It's magnetized. We call that magnetized. So that's the thing. So if you have a magnet, you want to stick it on your refrigerator, make sure that T is less than TC, or it won't stick. So this one won't stick to the refrigerator, and this one does stick to your refrigerator. And TC, I can't remember what TCs are. You can Google it. I forgot to write it down, and I don't feel like looking it up right now. But TC can be big. Like TC is greater than room temperature for certain materials. TC is greater than room temperature for some materials, such as famous ferromagnets. Of course, the most famous ones are cobalt, nickel, iron. Those are the most famous ones. So those materials have a TC greater than room temperature, so they are magnets, which means that their magnetic moments all line up at room temperature. Okay, well that's pretty cool. So that's the behavior of a nonlinear material, but there's a lot more to it than that. It is actually a very big topic. People spend their whole lives studying this topic. It's a gigantic topic. So let's go a little further, because there's something really interesting. The electromagnetism of magnets is kind of interesting. There's some interesting stuff that happens. Let's take a look at it. For example, let's consider a magnet, a ferromagnet, and let's suppose that we have T less than TC. So this is a chunk of iron at room temperature, and now it's all magnetized, right? So let's draw all the little magnetic moments. They're all the little dipoles inside are all lined up because of the exchange energy. Remember, the exchange energy is this: U equals negative J Mi dot Mj, where these are our nearest neighbors in the material. Nearest neighbors in the material, like atoms, nearest neighbor atoms. That makes all the spins or magnetic moments want to line up. And so that's the magnetization. I've drawn the magnetization of the material. But now something funny happens, because let's notice that if I just consider half of the material, I'll draw a dashed line. Let's consider the left half of the material. Then what does the left half do to the right half? And let's notice that these are dipoles. And so I can take this part and I can think of this as a big dipole. Big dipole. And so if this part on the left is a big dipole, then what is its magnetic field? Well, we know. This is what the magnetic field looks like of a dipole. We know. We derived it. It goes like this. Near, 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 right? And then it does the same thing over here. Near, near, near. You know, it has this kind of behavior where this is the B field, and then the B field is coming down like that. And so what we can do is we can ask ourselves, what is the effect of the left-hand side on the right-hand side? Now, we look, whoa, weird. Jesus Christ, what the hell? I'm sorry, I just did some weird mode by accident. So annoying. Okay, so we can ask ourselves, what does this B field do? This is the B field. So this is the B field of the left-hand side on the right-hand side. Well, notice that there's an energy, of course. U equals negative M dot B. And so we know that M, a magnetic dipole in a magnetic field, wants to align. M wants to align. And so that means that, notice how on the right hand side, the magnetic moments are pointing up. I'll circle one, they're pointing up. But notice how the B field is pointing down, the B field due to the left hand side. And so basically the left hand, you can see that B field makes it want to flip. M wants to align, then that means that M wants to flip. Wants to flip. And so that means that the material wants to demagnetize. And so we call this effect, we call this field that I just drew the demagnetization field. Demagnetization field. And it's something that you wouldn't have thought of on your own if you were just thinking, but once someone shows it to you, it's pretty obvious. It's like, oh my God, the thing wants to demagnetize itself. And so what the magnet really wants to do is this. The magnet doesn't want to stay all magnetized. The magnet wants to do this. We'll draw it like this. It wants to do like this. It wants to have these spins, or magnetic moments, are up and these ones are down. Because that lowers the energy. That makes this energy here lower and more negative. And so you can see it, because now this field comes up like that. And so now you can see what we get are these field loops. And this makes it happy, because now the magnetic field is going in a loop. And the magnetic moments are all parallel to the magnetic field. And that makes the energy lower. And so where this is the B field, you see it comes in a loop. But you know that this is at an energy cost. So this makes U equals negative M dot B is lower in energy. But you notice that something funny happens, because right here, there's something funny. Right here, I'll circle it at the edge. Basically, this is, well, I call this a domain. And then I call this a domain. They're two different domains. They have different magnetic moments. But then this we call the domain boundary. And you can see that something happens at the domain boundary. Because at the domain boundary, I have a spin up on the left and a spin down on the right. And so that means that U equals negative J M I dot MJ is higher. It's positive. It's higher at the domain boundary. The domain boundary. And so you can see that the demagnetization field makes the spins want to create domains. So the idea is that, so this is the bottom line. The demagnetization field creates domains. And domains means that the magnetization is not all constant. You have chunks. You have one chunk that's up, but it's next to another chunk that's down, which is next to another chunk that's up. You have these domains. And that lowers the energy. The domains lower the energy, but the domain boundaries raise the energy. Domain boundaries, they cost energy. So here, what the fuck? Stupid thing. So here, I will have this domain up and this domain down, but at the boundary, you see that I have the nearest neighbors are misaligned. So this is the boundary, the domain boundary. And at that domain boundary, I have U equals negative J Mi dot Mj for the nearest neighbors at the domain boundary is greater than 0. And so it costs energy, it has higher energy. So you can ask yourself, well, what is the final configuration of a magnet? What is the final magnetization of a magnet? And now you can get a sense for how complicated it is, because I have these two competing energies. I have the demagnetization field. I have the exchange interaction U, which makes all the spins want to be aligned. But then I have the demagnetization field, which makes them want to misalign. And so I get domains, and then I have the domain and the energy of the domain boundary, which is positive. So the way to think of it, you have the demagnetization field, you have the domain boundaries, and you have the exchange energy. Exchange energy, which is going to be my U equals negative J mi dot mj. And so these things all play out, and they compete with one another. And then you can make things even more complicated then what you can do to make things even more complicated is then you can turn on a magnetic field. And so now when you turn on a magnetic field, all of these things compete. All of these things are happening at the same time. So what happens? What happens when I turn on a B, then what happens to a ferromagnet? What happens to a ferromagnet? And so basically all these things play out. And so let's talk about it for a second. So the way, and I should say that usually what we talk about, we don't talk about turning on a magnetic field, a B field. We talk about turning on an H field, because H is the applied field we get from our free currents. So if we put a ferromagnet into a solenoid like this, and then there's our ferromagnet, and then we pass current through it, I, and then we're turning on some H field, then the question is what happens, all right? What happens? And so what we want to know is basically, this is what we want to know. We turn on H, and we want to know what is the magnetization. So what is magnetization is equal to some function of H. And what is it? What does it do? So let's talk about that for a moment. And so this is the way to think about it. Let's first consider, let's first consider the material at where H is 0. Let's consider what happens when H is 0. Now, when the applied magnetic field is 0, then what I'm going to get are domains. So I'm going to get, let's say I'm going to have a material, let's just draw, for example, 3 domains. So here I'll have a domain, an up domain, a down domain, and an up domain. And in fact, the magnetization could very well be 0, because the total magnetization could add up to 0. The total magnetization. Let's talk about that's what we want to talk about, is the total magnetization as a function of H. So then what we do is let's turn on the H field like this, through this arrangement, by passing the current through the solenoid. We're turning on the H field, and so then we ask the question, what happens? Okay, well, what does happen? I mean, basically, what you know is that when I turn on the H, then the M's want to be parallel. Want to be parallel to H. Right? The M's want to be parallel to H. And so that means that these guys here want to flip. Want to flip. But the guy in the middle can't flip, because the guy in the middle, if he flips, then he's going to cost a lot of exchange energy. So middle guy can't flip, because of the U is equal to negative J mi dot mj, because he has two nearest neighbors, and if he flips, then it's going to raise the exchange energy through this dot product. So he won't flip very easily, but the guy, so the middle guy can't flip, but the guy on the edge can flip. The guy on the edge, let's do it like this. The guy on the edge flips more easily. And when I talk about the guy on the edge, this is the guy on the edge. This guy is on the edge. And this is the guy who's in the middle. So the guy in the middle can't flip because he has two nearest neighbors. But the guy on the edge, notice that if he flips, it's gonna cost some energy, but he only has one nearest neighbor, so it's easier for him to flip, because he'll lose energy between these two guys, but he'll gain energy. The energy will be favorable between these guys. So if this edge guy flips, then he will be favorable. So if I call this guy 1, 2, and 3, then if the number 1 flips, then that will increase the energy between 1 and 3, but reduce the energy between 1 and 2. So he's easier, so he flips more easily. So the bottom line is that the guys at the edge flip. So he flips. The guys at the edge flip. He flips. And so you can see that if he flips, then it's going to cause this domain boundary. Jesus Christ. It's going to cause this domain boundary here. This domain boundary is going to move inwards. And this domain boundary is going to move inwards. You can see, because these guys at the edge flip. So as I turn on the H field, then the guys in the middle don't flip easily, but the guys at the edges flip. And so the domain bound, so basically turn on H, and then what happens is the domain boundaries move. Domain boundaries move to increase the magnetization, to increase M, because now you see that all the spins are going to start looking the same, and on this middle domain is going to become erased, and everything will switch. So I'll go from this case where I have spin up in this domain, spin down in this domain, and up. These domain boundaries will move in, and so then the thing will convert to this, where it's just a single unified magnetization. And so and that's when I turn on the H in this direction. So now if we look at the magnetization curve, where I have now the total magnetization as a function of H, then we see that if we start here at 0, so suppose that M is 0 in the initial state because of the domains, then as I increase the H field, then what happens is I can start increasing linearly. So my magnetization will increase, and that's because the domain boundaries move. But then at some point, all the domain boundaries are lined up, and that's called saturation. Saturation. And when all the domain boundaries have moved and all the spins and all the magnetic dipoles are pointing in the same direction, so my magnetization goes up, but then it flattens. And so then, so this is what's happening. But then now we're in complete saturation. Okay, so now we're in saturation. So I'll call this, it's flattened, so we'll call this saturation. Saturation. That's saturation, and that means that all these guys are lined up. Okay, now what do we do? Well, let's remove the magnetic field. Let's start going back. Now go back. Reduce the H field. And so now let's start moving in the opposite direction. So what happens? Do I follow that same curve? Well, I can, if I'm in the flat part, then I can go back and I'm still in the flat part because I'm still saturated. But what happens when I'm here, for example? What happens when I'm at this H? Do I just follow this curve going back? The answer is no, because in order to increase the saturation, we had many domain boundaries that were moving. But now, when I look at my sample, there are no domain boundaries. So I cannot just reverse I cannot reverse the situation because I can't just create all those domain boundaries because it's energetically unfavorable. Because remember, the guys in the middle don't want to flip. Middle guy doesn't want to flip. Doesn't want to flip. Want to flip. And so that means that as I reduce the H, it's just going to sit there. The magnetic moment, the magnet will just sit there, and it won't do nothing. It'll just stay saturated. Keep going into the erasing mode accidentally. It'll just sit there. And it won't. I'll reduce the field, but the magnet will just sit there. But then it will start to decrease. Why will it decrease? Because then the demagnetization will kick in. At some point, the demagnetization will kick in. Demagnetization will kick in. And I will start to flip. And what'll happen is, where will it flip? Well, it's really going to start flipping at the ends. Demagnetization, and then the spins will flip at the ends. So because the guy at the end only has one nearest neighbor, so the spins or magnetic moments will flip at the ends. Spins flip at ends. And then there'll be domain boundaries will be formed, and the domain boundaries will move in. Domain boundaries will move in from the edge. From edge. And so then the magnetization will start to decrease. And then I will. Oh, this is really annoying. It will decrease, and then it will start, but then I have to reverse the field, and then the whole thing will happen in reverse, and then the spins will flip, and then the domain boundaries will start moving in the opposite direction, and then I will saturate in the opposite direction. And then if I come back, the same thing will happen here. And so I get this kind of curve. I did not draw it well. I'm sorry. It should be more symmetrical. And so this is the curve. So it's a hysteresis curve. You've seen it before, probably. Maybe you didn't know what it meant, or maybe you did. But this is a hysteresis curve, and so this here, we call this the coercivity, HC. This is the coercivity. And this we call this the remanence, M naught, negative M naught, the remanence, because that's the part that remains when the applied field is zero, remanence. And so this is we call this hysteresis. And this hysteresis occurs because the magnetization is nonlinear in H. And you can see that it's obviously nonlinear because this is, if it was linear, then I would have MH is just a line, linear, boom. And it would go up and down this line. I would just slide up and down this line. But if I have, and so that's a linear material, so that would be, say, a linear paramagnet. would behave like this, but because I have a nonlinear ferromagnet, instead I have this funky hysteresis thing going on. But that's magnetization versus H, and where this goes in this direction and it comes back, and I can follow this loop. So this loop is the behavior of a nonlinear material, a nonlinear ferromagnet. And so for the linear paramagnet, I have the M is equal to chi mh. It's linear. But here for the ferromagnet, I don't have that. M does not equal chi mh, because there is no simple susceptibility. It's not a constant. Obviously, it's not a line. And so we get this, and this thing we call this hysteresis means that the magnetization depends on the history, depends on history, meaning that if I go forward and if H increases or decreases, then the magnetization depends on what you have done before. M depends on what happened previously, depends on what happened, on what happened previously. And so that's the idea of hysteresis. Okay, folks, I think that's a good place to stop. See you later.